Architectural flaws are particularly dangerous because they create systemic weaknesses that repeat across systems, teams, and releases, rather than appearing as isolated mistakes.
When a flaw is embedded in the architecture, every implementation that follows the pattern inherits the same weakness, often without realizing it.
This is why organizations can patch individual vulnerabilities repeatedly and still experience similar incidents year after year, because the underlying design assumptions never changed. Architecture shapes how systems behave under stress, how failures propagate, and how attackers move once they gain a foothold. If the architecture is unsound, even well-implemented controls struggle to compensate, and security teams end up treating symptoms instead of causes. Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Weak trust boundaries are one of the most common architectural flaws, and they occur when components or tiers assume more trust than they should. A trust boundary exists wherever data, identity, or control passes from one context to another, such as from the internet to an application, from an application to a database, or from a user environment to an administrative interface. When boundaries are weak, components accept requests without sufficient authentication, authorization, or validation, often because designers assumed internal traffic was safe. Attackers exploit these assumptions by entering through a low trust point and moving freely into higher trust areas.
Strong architectures make trust boundaries explicit and enforce them consistently, rather than relying on implied trust based on location or network placement.
Overprivileged services significantly expand blast radius when compromise occurs because they allow a single failure to affect many systems at once. Services are often granted broad permissions for convenience, especially when developers want to avoid permission errors during integration.
The problem is that when a service account is compromised, the attacker inherits all of those privileges instantly, often without triggering obvious alarms. Overprivilege also makes it difficult to reason about impact, because it becomes unclear what the service truly needs versus what it was simply given. Architectures that enforce least privilege at the service level limit damage by ensuring that compromise results in constrained access rather than total control.
Flat networks are another architectural weakness that dramatically increases lateral movement opportunities and accelerates the spread of attacks. In a flat network, systems can communicate freely with one another without meaningful segmentation or filtering. Once an attacker compromises a single host, they can scan, probe, and connect to many others with little resistance. This turns what should have been a contained incident into an enterprise-wide problem. Flat networks often emerge unintentionally when segmentation is deferred or simplified for operational convenience. Secure architectures treat connectivity as a deliberate decision, segmenting systems by function, sensitivity, and trust level to slow attackers and create observable choke points. Unvalidated inputs are a recurring architectural flaw because they allow attackers to influence system behavior through data that was never properly constrained. Inputs arrive through many channels, including application programming interfaces, file uploads, message queues, configuration values, and user interfaces. When inputs are trusted implicitly, attackers can inject commands, manipulate logic, or exploit parsers to gain unintended control. The flaw is architectural because it reflects a design choice to trust upstream components rather than enforce validation at boundaries. Robust architectures assume all external input is potentially hostile and validate structure, size, type, and semantics before use. Hidden dependencies create single points of failure and surprise exposure because they are not visible during design or review. A system may appear isolated, but it may depend on shared services, such as identity providers, logging pipelines, configuration stores, or third-party application programming interfaces. When those dependencies fail or are compromised, the dependent systems fail in unexpected ways. Hidden dependencies also complicate incident response because teams may not realize which systems are affected until symptoms appear. Strong architectures document and minimize dependencies, making critical shared components explicit so they can be protected, monitored, and tested appropriately. Poor key custody undermines encryption even when algorithms are strong, because the security of cryptography depends more on key protection than on mathematical strength. When keys are stored alongside encrypted data, embedded in code, shared across environments, or accessible to too many administrators, attackers often bypass encryption by stealing keys rather than breaking algorithms.
This is an architectural flaw because it reflects how key management was designed, not how encryption was implemented.
Effective architectures separate key storage from data storage, restrict key access tightly, and ensure that key usage is auditable.
Without disciplined key custody, encryption becomes a false sense of security rather than a meaningful control.
Insecure defaults expose services before protections are configured properly, and this flaw often appears early in the system lifecycle. Services that start listening on public interfaces, accept weak authentication, or expose administrative functions by default create a window of exposure during deployment and testing.
In fast-moving environments, that window can persist longer than intended and be exploited before anyone notices. This is an architectural problem because it reflects how systems behave out of the box, not how operators intend them to behave eventually.
Secure architectures favor deny-by-default behavior so that explicit action is required to expose functionality, reducing the chance of accidental exposure. Broken authentication flows enable session hijacking and identity confusion by failing to maintain clear and consistent identity state. Problems such as improper token validation, missing session expiration, weak binding between sessions and transport security, or inconsistent identity handling across components create opportunities for attackers to impersonate users. These flaws are often subtle and difficult to detect because the system may appear to work correctly under normal conditions. Architecturally, they stem from treating authentication as a feature rather than as a critical control that spans multiple components. Well-designed architectures define authentication flows end-to-end, ensuring that identity is established, propagated, and validated consistently across layers.
Inadequate logging is an architectural weakness because it prevents detection, slows investigations, and delays recovery even when other controls exist.
If systems do not record meaningful events, security teams cannot reconstruct what happened or determine scope and impact. This often leads to conservative assumptions, prolonged outages, and incomplete remediation. Logging gaps usually reflect design decisions made early, such as not instrumenting certain components or not centralizing telemetry. Architectures that treat logging as optional or secondary inevitably struggle during incidents because visibility cannot be added easily after the fact. Excessive complexity makes designs hard to test, understand, and secure, and complexity itself becomes a risk factor. Highly complex architectures have many components, many interactions, and many conditional behaviors that are difficult to reason about holistically. This increases the likelihood of misconfigurations, inconsistent controls, and overlooked attack paths. Complexity also makes security testing less effective because it is harder to model threats and validate coverage. From an architectural perspective, simplicity is a security control because it reduces the number of assumptions that can fail. Designs that favor clear boundaries and minimal mechanisms are easier to defend and easier to recover when something breaks. Weak segregation between environments, such as development, testing, and production, increases the risk of production impact from non-production activity. When environments share credentials, networks, or management interfaces, a compromise or mistake in a lower assurance environment can propagate upward.
Attackers frequently target development and testing systems because they are often less monitored and less hardened.
This is an architectural issue because environment separation is a foundational design choice, not a runtime fix. Strong architectures enforce isolation between environments and limit trust relationships so that experimentation does not threaten critical operations.
Unclear ownership allows architectural flaws to persist across releases because no one feels responsible for fixing them.
When it is unclear who owns a component, a boundary, or a shared service, issues fall between teams and remain unaddressed.
Ownership ambiguity also slows incident response because decisions and actions are delayed while responsibility is debated.
Architecturally, ownership should be explicit, with clear accountability for design decisions and long-term maintenance.
Systems with clear ownership evolve more safely because flaws are acknowledged, prioritized, and corrected rather than repeatedly rediscovered.
Architecture flaws multiply risk because they scale across implementations and endure over time.
Weak trust boundaries, overprivilege, flat networks, and insecure defaults do not affect just one system. They affect every system built on the same assumptions.
Hidden dependencies, poor key custody, and inadequate logging amplify impact by reducing visibility and control when failures occur.
Excessive complexity and weak environment segregation make it harder to contain damage, while unclear ownership allows known problems to persist.
When these flaws are addressed at the architectural level, security improves across the portfolio rather than one patch at a time.
This is why architectural thinking is one of the highest leverage activities in security engineering, because fixing the design fixes many systems at once.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.